I mean, so field of research for me, it was like, while starting, it was not much of, so to say, choice, because so I did my BSc from BHU, and then I was enrolled in MSc program at Pune University. So I wrote a lot of like exams after my BSc for these jam and all these things. So then I got I got through quite a few places, and I chose Pune University, and I finished 1 year there. And I really liked giving those exams for some reason, these objective kind of exams, and so they were good. But also at the same time, there was exam of TIFR and exam of IMSc, which was called JEST. So, and I really liked giving those exams because they had the mathematical flavor and they were asking questions which made you think instead of doing some just like quick calculations and so on. So I was just sitting in my class one day, no teacher was there in Pune University, and I see that the form has come up and there was no fees. The form was fully online, and I could just submit it and go for the exam. The exam was also in the university. And I just filled the form like that. I didn't think of anything. I didn't do anything. But then I got through the written. Then I'm like, okay, they are going to pay me for even traveling. So why not go to Chennai? I've never been to Chennai. So then I go to Chennai, and then I realize, okay, this is a whole new world. So I didn't choose the area so much as it happened, at least the beginning of me getting into a PhD program. And why I wanted to do a PhD was like, I was just like, okay, I don't want to do a 9 to 5 job right now. Maybe I want to explore something more. And that was that. It was not that I thought that I'll get into graph theory, I'll get into graph algorithms or anything. Then after getting into IMSc, it was okay. The coursework was very rigorous. The professors were very nice, and then they started teaching, and then the whole field started opening up. And and then like okay, I found that okay, I have this affinity, so to say, towards like graphs and algorithms. So that's when it got decided. So I think. I mean, we all come from like different environments, different like we are all products of our own whatever. There are so many factors that just giving one path for like to everyone to decide what they want to is hard. But generally, I would say that explore as much as you can different directions and let your curiosity lead the way of where you want to end up rather than being like deciding because see people say that okay, I mean theoretical sciences there's not much scope. When I was in VH1, one professor like he was like, oh, you want to go to TIFR, you want to go to IMSc, but they only do theory there, what will you do? So but then like if you are interested in something and if you are curious about something, then whatever small that field might seem initially, when you go into it, like new avenues will open. And so yeah, my suggestion would be to let just like your curiosity lead the way instead of defining beforehand, and have a feel for things before deciding for that okay, I want to pursue this particular field on. So I hope that like sort of. So I mean, so there are some funny introductions also that I've come across. I mean, so I also say I count things as a job. So generally, what happens is, so there are some things we are all used to computers. They're used for a lot of applications and so on. But there are some things that the computer cannot do, and that you prove theoretically. Then how fast like all our systems differ. Somebody is sitting on a Mac, somebody is sitting on some other laptop or a desktop or whatever. But there is some fundamental way that if a program runs on a Mac or if a program runs on any other computer, there is some way that all these are going to be similar, and that is going to be number of steps. So then it does not matter how fast your processor is and so on. And so if something is slow on a Mac, then in some way it is going to be slow on some other computer also. So then, how do you study these things? How do you study how fast a program can run? How do you study that, okay, can we push it even faster, or it's not possible to do it even faster? Like if something is taking 3 seconds, like can we do it in 2 seconds? Can we do it in 1 second? And how do you study those things, that how far you can push? Because there must be a point beyond which you cannot push. So that is what, I would say that is what theoretical computer science does. That it tries to study the problem, whatever a computer can do from both the directions, that how fast we can solve it, and what is the lower bound, like what is the limit beyond which we cannot go faster. So that is like, yeah, I think that's an introduction to the subject of theoretical computer science. It is about limits of computation, and so on one hand it's about limits of computation, on the other hand it's about efficiency of computation. So these are the two things, like one side just tries to bring the efficiency more and more, so it tries to reduce the time more and more, and the other side tries to push the lower bound up and up, and yeah, so that's the idea generally. So whatever algorithms we design, we have to do their analysis, right? And that's the idea, that we want to design faster and faster algorithms. And for that, we need like these analytical tools and so on, that, okay, how do we analyze that, how much this algorithm will take? And then there are these asymptotic notations that basically, I mean, it does not matter that, for a fixed size input, what it does. How does the algorithm or its running time scale with the input size? And that is the main thing that is studied and so on. So yeah, I think it's quite interesting. There are other things also, like, there are some people who are working on. So this is like, I basically, I got a bit biased in explaining theoretical computer science. And so generally it is divided into two things, like it's called theory A and theory B. So theory A is generally algorithms and complexity. So algorithms is basically making efficient algorithms, and complexity is, trying to show that efficient algorithms cannot exist for certain things, and these complexity classes like P and P and so on. So this is theory A. There is another part of theoretical computer science, which is theory B, which is about logic and automata theory. So which talks about, correctness of programs, or, modeling computer programs in different ways, and what can be decided, what cannot be decided. So that is more close to logic. So that kind of work is also done, and all these theorem provings and stuff that comes in theory B, and theory A is more about algorithms and complexity. So yeah, this is a bit more technical. The earlier one was a bit more naive. Yeah, that's true. And I mean, it's unfortunate in a way that it is not like, even at a introductory level, it is not taught, at undergraduate, because I don't think the concepts are, they are abstract, but they are not like, they don't require something very complex to understand. Like, the machinery is not very complex. The thought itself, or the, like, uh, it can be abstract a bit, but the machinery is not too complex. So it can be, taught to even undergraduate students, or like just the basics, that, okay, this is what is. And then they can be interested, and they can pursue the career and so on. Because if you, I've seen like many theoretical computer scientists, or who also go then and become very good coders, because they understand, they have the like toolbox of designing, like, very good algorithms, and they, like, excel in those fields also. So, but yeah, I mean, some things are not in our control, so it's hard. So graph theory, basically, I mean, graph theory is just a modeling tool, or that's how I see it. That, okay, I mean, you have some problem, and you want to abstract out the relevant things. You want to, like, don't worry about a lot of. So there's this very famous bridge crossing problem, which is there. I don't remember the city's name. That, okay, there is this city and there are a certain number of bridges, and people want to know whether you can go from one point go to every bridge exactly once and come back to the same point. And this was asked as a problem, and this can very easily be modeled as a graph problem by putting each side of the bridge as a vertex and so on. So I think graph theory is an abstraction which allows us to see the inherent structure of many of the things. So there are so many things that can be modeled as graphs, you have road networks, you have internet, you can have a vertex for every page, and then you can have a directed edge if page A, links to page B and so on. You can have a graph of Facebook where every two people in the friend list have an edge between them, and the vertices are the user base of Facebook. And since there are so many ways in which we can use graphs to model things, the applications or the computer science applications also become very vast. Now, just imagine that, okay, the problem is that you want to find, certain set of people who don't know each other. You want to find a large such set, or you want to find a click on the Facebook graph where, a large bunch such that all of them know each other. You want to find, okay, how many, if I want to go from point A to point B, if I want to reach from person A to person B, and I can only move through their friends, how many hops it will take for me to get there? And all these problems, when you abstract it out as a graph, then they become very easy. So now, so this is just the modeling part of graphs. That okay, now we have a problem, we can model it as a graph problem. And then the computer science or the theoretical computer science thing comes in that, okay, now how do we solve it? What is the optimum algorithm to solve it? And can we make it faster? Can we so then all these problems like Hamiltonian path, can you go through all the, so you are given many cities, and you are given some links between the cities, and can you go through each city exactly once and come back to the same city? Hamiltonian cycle problem. So yeah, I mean, so this way, which is again, there is no efficient algorithm known for this problem, and people are still it's still open whether there can be an efficient algorithm for a lot of problems. So I guess that graph theory and computer science is get related because of the applications or the large number of applications that the graph theory itself has in terms of being able to model things. And when you are able to do that, then you see that a lot of real world problems reduce to some basic structures or in graph theory. And removing these additional things and getting to the core of the problem, I think is what the essence of, in some sense, mathematics is. That okay, you remove everything and you abstract out, okay, that this is exactly what is the problem. So that's how I think that these two interact, graph theory and computer science. It's as vibrant as it can be, and I mean, P versus NP is there anyway. Everybody knows it, but there are so many other conjectures, hypotheses, which people don't know if they are true. There is this thing called exponential time hypothesis. There is strong exponential time hypothesis. There is this thing about matrix multiplication, whether it can be done, in n square time or not for n cross n matrices. There are so many. There are so many conjectures. There are important problems. There are, so again, in complexity, not just P versus NP. Then there are many other classes uh, which deal with different models of computation. So this P versus NP is about Turing machines, Turing machine model of computation. Then there is another model of computation called circuits, where you just have these and or not gates, and you have a bunch of inputs, and then you get one output, and then there are similar classes to P versus NP there also, and then whether they are equivalent, and I mean, yeah, it will. It is yeah, sort of futile to mention just a few problems of which are open, but there are like a lot. And for students, I guess like this field is, the theoretical research will go on till like these problems are solved. So it's not that the scope or whatever these things are going to be any less. And so the students can look forward to solving many of these problems, and uh, that can be one thing. But also, I feel that uh, gaining theoretical knowledge about the algorithms and computers in general also makes one well equipped for doing applications. Because, for example, the theory of NP completeness, it's all about reductions. How can you reduce one problem to another problem, and so on. So when you get a real world problem, and you you know already how to solve a bunch of problems, so you should know how to reduce this problem to, if you can, then you should know that how to reduce the given problem to one of the problems that you have already solved. Otherwise, every time you will be starting from scratch when you're given a problem. So these problem translations, and sometimes the problems can look very, very different, and still the underlying mechanism will be the same. You can reduce, if you can solve one, then you can solve the other. So, and theoretical computer science makes you aware of such, like reductions and such tools and techniques. So, and if you're designing an algorithm, like you should, like not try to design a polynomial time algorithm for an NP complete problem, and so on. So such things also, like if you have studied. So this I'm telling from the point of view of applications people, why they should, like if they know a little bit of theoretical computer science, this will help them. But theoretical computer science as a field itself, it's quite vast, and a lot of research is being done in a lot of universities. Like there is, well, of course, all the big universities like Harvard and Stanford and Oxford and whatever they are doing, and but even like some small places in India, it's not happening much currently, but it's expanding. Like earlier, only, let's say, IMSc, TIFR, and maybe IIT Kanpur and IIT Delhi used to be the like only places where research was done in theoretical computer science. I mean, I might be forgetting some names, but more or less these were the hubs. But now it's expanding, and now there are some very good theoreticians in like many other places, many of the newer IITs, and more people are joining the established IITs, and so on. So yeah, I think it's expanding even in the country and even otherwise. I used to joke about it, sort of, that after not finishing, I didn't finish my MSc, and I joined MSc. So I was there for 1 year, and in my first year of MSc, so it was in computer science at Pune University. So we were made to, like do a lot of programming. There was operating systems, there was data structures, there were all these courses and so on. But somehow, and I'm not like bragging about it or saying it's a good thing and so on, but I didn't write a single program in the next 10 years of my like academic journey. So it's not that programming is something very like necessary for working in theoretical computer science in any sense. In fact, we also talk about that theoretical computer scientists will have to come out one day and say that they are mathematicians, like they are just fooling people by calling themselves computer scientists. But I mean, so that's an inside joke about the theoretical computer science community. But I feel that the everything is of very, very mathematical flavor in theoretical computer science. So I don't think there is any handicap of somebody who has not done programming. So I mean, and I'm taking the background question in sense of programming only, because I don't see that what else a computer science person would have done that would give him or her an edge. So yeah, to answer the question, I think it wouldn't be very hard for somebody who's mathematical. In fact, it will help a lot. So what happens a lot of times is that somebody who has done programming will not know a lot of the mathematical tools and techniques. Like linear algebra is used a lot in theoretical computer science. And there are a lot of other things from mathematics which will be used in theoretical computer science, which a programmer might not be aware of, and they might not even need it in application fields. But since here you are dealing with abstractions, here you are dealing with the theoretical limits of algorithms and so on. So there you will need these mathematical structures, and people from mathematics will have an edge, I feel, in some sense, over the others. Yeah. So teaching is more of how to say, uh, you don't have like a lot of control over what you're going to teach, because you are at a place and it has certain requirements and so on. And then I take whatever is there and try to see from there and teach. So like I'm teaching operating systems, but I said I have not done programming for a long time. But it's fun, it's nice to get back to certain things, to learn new things, to explore them again and so on. So it's good. So as I said, that teaching is more of a it depends on the circumstances, that okay, where you are, what you're. So but in research, I basically my area is called parameterized algorithms. So you might have heard of these NP complete problems that so generally we divide like efficient and inefficient in terms of like polynomial time and no polynomial time algorithm. So these NP-hard problems, they are not known to have any polynomial time algorithms. So then, and polynomial time algorithms is what we call efficient. So then there is this question that, okay, so do we just leave those problems? What do we do with them? Because they arise many times in our like real world applications and so on. So then the question is, okay, like, there should be some way to deal with that. And there are like, there can be multiple approaches. So one of the approaches is like approximation algorithm, where we say that, okay, give me a solution fast. You don't have to be completely correct, but do it quickly. So if the answer is like 100, you can give me 101 also, and I'll be fine with it. But don't take like, too much time. Don't take exponential time. The other approach, which I work in primarily, is called parameterized algorithm, where we also have some more information about the problem. So you are given the problem and you are not just given the input like instance, you have some extra information. So the running time of the algorithm is not only going to be measured in the input size, because generally we know something more about the input than just the input size. So if there is something about the input that is small, some structural thing that, okay, this is a road network graph that I'm given. So then it will be a planar graph or something. Then I can exploit that information that, okay, it's something is going to be, some parameter is going to be small. And then what we try to do is try to get an algorithm with running time f of k polynomial in n. And n was the input size and k was the parameter. So k is small. So this f will be exponential. So the exponential blow up will be confined in uh, k, which is small. So you get exponential of a small number and polynomial of the big number, which is n, which is the input size. So still the running time, like, is efficient somehow. So this is one way to deal with NP completeness, and this is what I work in. Another related field that I work in is called kernelization. So this is like parameterized complexity that, so generally in classical complexity, what happens is that the running time of an algorithm is only measured with respect to the problem length or the problem size. That if the problem size is n, then running time of algorithm is basically f of n, some f of n. In parameterized complexity, you are given another parameter apart from the problem size. So it is f of n comma k basically, and then you try to minimize that. So that is a more high level view of the field, that it is multivariate complexity instead of a single variate complexity. And then the the whole interplay that happens between them. Another field is called kernelization, which is like we are given a problem and there are some things which we can remove and make the problem small. So we are given a large size problem and we want to like remove some easy part, do this in polynomial time. So we are given an NP hard problem. So we cannot solve it in polynomial time, but in polynomial time we want to make it small. We want to get rid of the easy part so that we can get to the kernel of the problem. So that is another field is called kernelization where I work. So this is in a nutshell, introduction to fields. Yeah, I was thinking about this. I mean, it's a hard question. It's because I mean, after you have seen the system up close, then you also see that any change you wish to make is not you can't make it out of thin air. So people are trying to do their jobs, but the problems are so many. There are so many structural problems that if you don't solve them, then other things won't come up. And if I'm asked to daydream, I can just say that okay, I want more quality education. I want more colleges which are providing nice. I want better teachers in colleges, and the list can go on and on. But it's very hard to actually come up with a solution in terms of let's say an effective thing to say which can be implemented in a nice way. But one thing that I would say is the education in general in colleges or can be a bit more knowledge or curiosity driven rather than just job driven. But then again, as I said, this all goes down to the way our society is structured, and the what is the primary goal of education, that people want to get jobs, and there is this whole insecurity that if we don't get jobs then what will happen, and so on. So that is why, so it's all so much interrelated that of course I would change many things, but then if one asks how to go about it, I might not have a clear roadmap to how to do that, because I could not solve a problem that we were working on. And he was like, okay, why do you look so dim? What happened? I was like, I've been thinking about it for so long and I'm not able to solve it. All day I sat and nothing happened. And then he was like, okay, so how many papers do you want to write in a year? I was like, okay, what kind of question is that? How is that related? He was like, no, tell me. I was like, when you will be happy? What number will make you happy? I was like, anything, even 2 papers a year is good enough. At that time, student, and then yeah, that should be. Or if I'm doing very good, maybe 4 papers, 6 papers, I would like to write. He was like, okay, so suppose 6 also, suppose 10. In a paper, how many ideas do you think there are? How many these new ideas are there in a typical paper that gets published? It's like 1, 2. It's like, yes, if your paper has one new idea, then it is already a good paper. Because a lot of papers are just applications of existing ideas. So if it has one new idea, it is good. If it has 2 new ideas and it connects them, it's very good. And if it has 3 or more, then it's at the top level in the field, and you are getting published at the top level conferences. So if you are having 10 papers, then you require these 20 ideas, let's say, on average. And how many days are there in a year? There are 365 days. So out of these 365 days, there will be maximum of 20 days, even when you are very successful in your field. There will be maximum of 20 days when you will have this idea which will make you go forward. The other 345 days are going to be just this thing that you just sit on a problem, you keep thinking about it, nothing happens. You sit on a problem, you keep thinking about it, nothing happens. And that is the hard part. That is the hard part about the PhD. That, okay, still keep going back to it, still keep trying it. So to have that much of motivation in yourself, or some external motivation, whatever it is, but one has to be able to do this to get a PhD, at least in my field. in some other field, there might be some other ways to do it. But this is one thing that, at least in theoretical computer science, is that you have to keep getting back, at the problem. So you have to be quite stubborn because the problems are also very stubborn sometimes. So they don't give way, you don't give way, you keep fighting. One day, you'll crack them. There's this whole philosophy that you have to keep the problem in your head for a long time. And so the authentic the mathematician, one of the great mathematicians, he used to say that I just keep the problem in my head, you keep something something edible or a fruit or something. I don't remember the exact this thing, but the whole idea was that, okay, with time, the outer layers, get dissolved in the water or whatever, and then you get to the crux of the thing. Uh, and that's what. So you have to keep getting back at it, and that is the most important thing. Of course, there are other parts that come that, okay, you should keep updating you with the existing research, and whatever is happening, you should be reading the current research papers and all that. But I think the most important part is perseverance in PhD. So yeah, I mean, it is actually quite a quite debated question, but I personally don't think that it should be debated that much because so there is this notion of correctness of a program, right? We all the time prove correctness of our algorithms. Okay, and so if now you have some suppose you have multiple cases which was in the case of Fourier theorem, that you have a lot of cases and it's you cannot enumerate all of them by hand, and then you write a program to enumerate them, and then the program does something simple which can be verified by the code of the program. So you can look at the code of the program, prove its correctness, and then make it go through the cases, and then whatever output it does, it's fine. I mean, I don't see why just because a computer is being used, it should be called and then you can, of course, then there are these questions about, okay, what if the hardware is faulty? What if run it on different computers then and see yeah. So on one hand, just do the correctness check of the algorithm or whatever it is theoretically. On the other hand, run the program on different hardware and so on, and then it gives you I think reasonable certainty. Even the handwritten proofs that we talk about so much in mathematics and so on. It is what convinces other mathematicians. A proof is what convinces other people. I mean, it's not that every time somebody writes a paper, they are going through the whole Turing machine description to write their papers if they are writing a paper. So I guess, I mean, there might be some other philosophical objections that I am not very fully aware of, but from what I know, this seems to me that okay, why they shouldn't be allowed, they should be. So that's my take on that. I don't see why they shouldn't be. So I feel that it's. I mean, if the program can be verified that the program is correct, and then you can use different compilers, you can use different programming languages to code the same program and then see the outputs are same. So if the algorithm is correct and then you have verified it in different languages, different compilers, different systems, then I don't see why such a proof which has such a part for enumeration or for going through certain things, then why it shouldn't be accepted. I don't see any reason. But yeah, on the other hand, if it is just used to bypass certain things and it's not clear that the program is correct, then of course such things should not be accepted. So the rigor should be there in checking the programs and doing the experiments on different kind of systems. And I have talked about it before also, I guess. I mean today, but. I mean, depends on the area. It's it's very subjective. Like as I said, I did not need to do any of programming in all of my career as a theoretical computer scientist till now. Similarly, a person who is doing certain kind of programming or but will not need to know quite a few times that what is the algorithmic complexity of this program or whether so it depends on like where you are working, it depends on the context, it depends on like what kind of problem you're trying to solve. I think it's helpful in general if you know certain things, but I won't say that this is a necessity for anyone to like know both the things. Yeah, these are hard times. I mean, we as even teachers struggle with the same. That even our interest in things, our research suffers because of this. Our because we are not interacting with people face to face. We cannot write on blackboards, and the other person is seeing us writing and talk. So it's very hard. But I mean, and I wouldn't say that there is some magic way to keep it at the same level as it would be in a completely offline way. But I mean, there can be ways like talking to your peers about the things, looking for resources even online that you like just so nowadays there are many like YouTube channels and stuff where so I was just talking to one friend about this amazing channel called Three Blue One Brown. If you guys have seen it, it's very nice. So it animates like different mathematical concepts and teaches them in a very visual way, and it's it's quite amazing. So, I mean, there are such resources now, and one should go. And still, one thing that I think might uh, help is like we try to like be as close to what you used to do in the offline mode. Like, don't like do classes while lying in the bed. Like, be on a table and chair for taking classes, because that also affects the kind of mental state you are in if you are just lying down and you're just lazing. And so just like to be in a proper mental state, try to be separate your if possible. Again, it's not possible for everybody, but try to separate like your work and whatever rest place a bit, so that try to follow a schedule. So these things help a bit in certain things, and then try to I mean be interactive in the class, because like as a teacher I've been facing this problem a lot. Like students are just I'm teaching blank screens, and I don't get any feedback, and I'm like it sounds very monotonous, and it's hard to for even teachers to keep interest in teaching the classes. And like you keep saying ask questions, everybody thinks that everybody else will ask questions, nobody asks any questions. So I mean this is hard, but I think if even in classes if you become interactive, then it will help you also and the teacher also. So there is a selfish reason for saying this also. But talk to your peers, try to see as many resources online as you can. But even after all that, like maybe it will not be possible to get to the same level of enthusiasm, because like this will affect mental health, and then I mean it's very much possible, and then I can understand that because that has happened to even me to some level. So we can just try to do our best in such bleak situations. So these are some of the tips, so to say, that the students can employ. I'm not sure exactly in theory it will help or not, but I mean I think it's good, because see, computers are now getting to like it's getting to a point where whatever you do, the basic knowledge of computers is going to be like quite necessary. It's the world is like without a doubt going into that direction. If you don't know computers, you don't like life is going to be very very hard in terms of employability and interactions or whatever. It's going to be very very hard. Now coding, I don't know what exactly the kind of coding they are planning to teach, like in sixth or so on. But like I personally feel that the theoretical things can be taught a bit earlier to students. To kids rather than. I mean, the whole like logic and like math syllabus, I feel can be uh, made a bit more like not focused towards computer science, but something that leads to concepts of computer science in a natural way. So if you have like a bit of discrete maths, a bit more of like discrete maths, like you have sets, etc. It is taught at some point, but then it just doesn't make sense. Like what union intersection? It's like then you tell these things. Maybe a bit of logic, I feel can be taught. And coding, I mean, it's fine. I think it's good only that they are planning to teach it. I don't know how exactly it will be implemented, but the idea I think is good that to start teaching coding, and I think the students will benefit only from it because it is. I don't see it in terms of that it will help them in getting a particular job, but then I feel that it will contribute towards the general computer literacy that is going to be the need of the hour, like, after some time. Or it is even now. I mean, PhD there are, you can just look at Ivy Leagues, they are there, of course. So, and I mean, more than me, I think a simple Google search will give much better answers. But I mean, if you just want to get some names, like then all these Harvards and Stanfords and Oxford and Yale and all these are there. But I guess like this question, I will not be that equipped because again, okay. So instead of answering this question very directly, let me like try to like sort of indirectly answer it because so one thing is that there is no one good university for PhD in general. I mean there are some universities which are generally very good and so on. But when you are going at PhD level, then there are a lot of other things that become important, which is like, okay, so do you have a potential advisor in mind? What area do you want to work in? Does the university provide an ecosystem for that particular area? And so on. So these things become more important than like the university name. So for PhD, generally the university is not like I would say that should not be the only deciding factor, or maybe even the most like important deciding factor. It should be the area, the faculty, the yeah, so on. So more than that, I would say that going by the university name, like look at the faculty profiles, what they have been doing, their research areas, and maybe talk to some of the students which are already there or who have graduated to get to know more about the research experience at that university or the PhD experience at that university, rather than just going for some university names. I mean, depends. See, while you are doing your masters, then you should like definitely get in touch with some of the professors and do some research. Try to do some research. At least read some papers in the area. You should narrow down into something. So you should not be completely clueless about what you are going to do your PhD in. So that is one thing that okay, you have had a feel of you do your undergrad, you do your masters during that time, or if you are an undergrad, then do a masters to get a feel of different fields and then decide what to do read the research papers, do try to see like, what are the problems people are working on. Look at the profiles of professors who have been working in those areas and try to see that what matches your interest. And again, it doesn't have to be that you have to understand everything, but you should get like, at least some idea of what is going on in this field. Talk to other students, that always helps, like who have already enrolled in a PhD or who have finished their PhD. So, I mean, these are the general pointers, but just like try to have like, whatever coursework you're doing, try to do it well. Have a very good understanding of whatever is being taught. Read books. Like reading a book from cover to cover is something that like is I cannot emphasize less upon. Like, it's if you can solve like, most of the problems in a book and you can say that, okay, I have read everything in this book, then like that gives you a lot of confidence and a lot of like, it's just like generally, I'm generally talking about good books. And if you have like, then it's just like takes your confidence, takes your knowledge to another level. So read books, read about things, explore things. So that's the general idea. Nothing very specific. Abroad, again, like so that whatever I said works for doing a PhD, like whether here or abroad. I don't see what like should be different in case of looking for a PhD abroad. And maybe there are more places. There will be better places abroad. There will be like more in number that one will be applied to. But I think just for going for a PhD and going, it should be the same. The um, process should be the same. It's not, I don't say like, that depends on the university you are applying to, that depends on the professors there. And I don't think there would be any such hard and fast, like, it always helps. It definitely helps if you have done a research project. That's what I was saying. That if you have acquainted yourself with the current research that is happening, or with like work with some professor on some research problem, that always helps, and that will give you some like uh, edge, so to say. But I mean, again, saying that it's an absolute necessity is not something that I would say. It's I've seen applications which go through because the student has just worked hard on his or her own and then like has applied. But yeah, getting because again, if you show your zeal, if you show your interest in the subject to your professor, the professor is also more likely to give a nice recommendation for you, which is also quite important in some cases. So all these things are there. So, but again, there are many factors, and it's for getting through PhD position. And again, those factors will come as a byproduct if you have enough interest in a field, if you are doing some work, if you are reading some papers, research papers, if you are putting in the hard work, then you will secure an admission. Yeah, I mean, so I've been mentioning the problem, but if one is to define the problem, so uh, okay, so I've said a lot of things. So generally, as I said, the algorithm's running time is measured in terms of input size. So now we all know growth of functions, that polynomial functions grow slowly, exponential functions grow fast, and so on. So we say that a problem is efficiently solvable if it is if it has a polynomial time algorithm. So polynomial time is good and exponential is bad. Let's say. So polynomial time algorithm is good algorithms. So now there are a bunch of problems which nobody knew how to have a polynomial time algorithm. And then what happened was that, and still nobody knows for any of them how to have a polynomial time, how to solve them in polynomial time. Nobody knows. And then in one breakthrough paper, like what like there was a guy named Cook. So it's called like NP completeness. The whole theory of NP completeness comes from there. That all these problems which were hard, for which no one knew the like how to solve them in polynomial time. There were many of such problems which could reduce to each other. That if you can solve this, you can if you can solve A, then you can solve B, and if you can solve B, you can solve C, and the whole chain was created. And this chain was like circular in some sense. That now, if you could solve any problem in this set, then you could solve all of them in polynomial time. So, and these problems came from like very different fields, like something will be from scheduling, something will be from graph theory, something will be from the like very different fields. So, but still they were related. They like, if you could solve one of them in polynomial time, you could solve all of them in polynomial time. So these were the NP complete problems. So now the question is, the P versus NP question is that can you solve any of them in polynomial time? If you solve any of them, then P will be equal to NP. Or you show that they cannot be solved in polynomial time. So then you will show that P not equal to NP. So this is the this is the Millennium Prize question, that whether either you show P is equal to NP. There are these two classes. So P is the class of problems which have polynomial time algorithms, and NP, to make things simple, these hard problems. NP are these hard problems, a bunch of problems which are all interrelated. And P is the set of polynomial time solvable problems. And we don't know whether these hard problems can be brought back to the set P, whether they belong to the set P or not. And the thing is that even if one of them can be brought to set P, then all of them will be brought to set P. So this is one possibility, that they are shown to be in P. And the other possibility is that you show that, okay, exists some problem there that cannot be solved in polynomial. So then all of the NP complete problems cannot be solved in polynomial. So then you would have separated P and NP. So this is the question. And then like similar to this, there are many other questions. So these complete problems have their own theory, that every such complexity class, there is this whole theory of these things. So this basically gave rise to the field of complexity theory, this paper that I'm talking about. So it's quite interesting, and like I would urge you to explore it more, PNP, and even like in general complexity theory. Maybe I'll offer a course also on that at some point in time.